Hi, so I'm George Miley. I'm Professor Emeritus at the University of Illinois. Now, I've been involved in this field, space power, for many years. One of my specialties over the years has been alternate concepts, or a lot to do with fusion propulsion. Fusion is bogged down at the moment because we have the magnetic fusion tokamak project, which is international in France, and we also have the laser fusion project, which is at Lawrence Livermore. Problem is, both of those projects have such large devices. What has to be done is the development of smaller fusion devices. I've focused a great deal of my effort on inertial electrostatic confinement. It uses electrostatic fields to confine the plasma. Now, there's a theorem that says you can't do that, but if you add the word inertial in, you can, because then we have the ions running back and forth. It's the inertia combined with the electrostatic forces that confine the plasma. Another virtue of inertial electrostatic confinement devices are that they're very simple to build. More high school students have built those devices than anything else. And so if people are interested in it, they can read this book, published by Springer Press. So it's called Inertial Electrostatic Confinement Fusion. But the great thing about it is that you can have a fusion propulsion system which has a tremendous ISP. Now there are some other small fusion devices that might compete with that, field reverse devices and so on. We need to study this. NASA, with their NIAC program, had, I think, about 5 projects related to this type of thing. When I retired, my students asked me why I worked on so many different things, ranging from nuclear pump lasers to low energy nuclear reactions, which I'll mention in a moment. I wrote a book which I'll tell you about real quickly, called Technologist Searches for a Black Swan. I said I've been searching for a new energy source, which is like a black swan for me, and I'm enjoying the search even today, but I haven't quite gotten there yet. Now, the low energy nuclear reaction business I'm talking about here is an outgrowth of cold fusion. You didn't have to have hot temperatures of plasma like I work on with inertial electrostatic confinement fusion. You can do it with cold solid state materials. So really it opens up a whole area of condensed matter nuclear science that the next generation is going to enjoy working on, because I'm convinced that the physics is there, or I wouldn't be talking about it here. And the real question, can we develop it? What we do is we take a material like palladium, let's say, or something that can absorb deuterium or hydrogen, and we stress it so we create many defects in it, and then diffuse, say, deuterium into it. The deuterium enters these defects and does what we call a sort of a Bose-Einstein condensate into the region where the defect occurs. And we're going to have very high density. We have maybe 1,000 atoms of deuterium forming sort of a new lattice within the palladium lattice. This new lattice is created in the defect that will fuse if another deuterium comes into that cluster and transports momentum, and that's a sort of a simplified view of what's going on in our types of systems. So we currently have demonstrated this for up to several hours. Our problem at the moment is a materials problem of keeping the material holding together long enough to have a practical system.